Yeah, but if you look and see if you can find the biostats or like epidemiology. I'm not exactly sure where there'd be, but there's some really good courses there as well. Okay. It's great. So let's get started. So today, I'm going to be talking about outliers and kind of like robust estimation. And so how to deal with when you have various sorts of noise in your data. So let's start by, let me just review the schedule a little bit once more because there's been some recent movement. The dimensionality reduction homework is due on Wednesday. You should have had now, I think, plenty of time to do that. And then this needs to be updated, refreshed. Okay. And then we split homework assignment 6 into 2 parts. The part on noise and outliers and anomalies and stuff will be due a week later on Wednesday. I should be able to, I drafted it. The TA is reviewing it, so it should be up fairly soon. And then there'll be another small part on graphs due at the end of the semester, right before the test, so you can kind of force yourself to do it before you take the end-term test. So a reminder, there's confusion about it. The end-term test is indeed on the last day of class, not as was, I had the wrong date on Canvas, unfortunately. So that's there. Yeah.
Is it going to cover from midterm to end term, or?
Yeah, it's going to start with I stopped the midterm before the streaming section, so the streaming section can be on the end term as well. So everything up through there. There could be some concepts that build on earlier stuff in the semester, so like anything is fair game, but the point would be to evaluate you on the topics we covered since what was covered since the material covered by the midterm, not since in class since the midterm. And then the final exam is actually the poster. So the poster presentation. So this is during the final exam slot. Okay. So if anyone asks, it is not. It is, for university policy, that is the final exam. But that gives more time for that poster presentation, which should be a lot of fun. Okay, so we're starting kind of a new section of the course, although probably the feature selection stuff kind of nicely blended into this on how to think about noise in your data. So we've been talking about modeling and structures. You can find probably ideas of noise were present in this, but we'll be talking about kind of mostly three different topics in here. One is kind of how to deal with outliers or how to robustly estimate things so that outliers don't affect it as much. Second one will be on doing anomaly detection. So what does this mean when it's different than looking for outliers? Sometimes an outlier would be like anomaly detection, but we'll kind of give a perspective on this. This will be a bit more statistically motivated. And then we'll talk about privacy. And the way we kind of formalize methods for dealing with privacy is you basically are kind of adding noise into the data, but in a kind of structured and careful way. So you can trade off the amount of noise you've added in with the amount of privacy you've preserved in the process. And so we'll kind of, that'll be some of like a historical lecture as well. We'll go through kind of the history of how that's happened. And then we'll get into the graph stuff. And this lecture will be kind of an ethics focused lecture, and we'll do some sort of class activity in there as well, the one between graphs and noise. All right, any questions on the schedule? Will seem clear. Okay. Yeah. So outliers and noise, let me start by talking about kind of the types of noise. And I like to think of kind of 3 different types of noise, just so it's kind of, you handle them in kind of different ways depending on what you mean by kind of noise. The first one would be like these spurious readings, or if you're sensing data. So this would be like a sensor malfunction, like if you have a sensor you're reading data from and there's a malfunction in there, or if you kind of like a mislabeling of something. I mean, sometimes data gets encoded and it's just wrong. It's got, it's supposed to be 10, it's like, and it's like 100 million. You get these data points which are just like completely off from what you would expect or is possible. And so these are kind of the issues that we deal with, like outliers. Okay. There's another class of noise, which would be like the measurement error. But this sort of error is kind of often normal. Okay, so it's not unexpected error, but it's kind of like mild error. Okay, so if I'm trying to read a point here, this is the true value, and instead I observe the point so someplace nearby. Okay, so I don't get the exact value, and I get instead an observation of it, which is nearby the true value. Okay, so if this happens, okay, this is kind of standard, but we somehow need to deal with it. And so when we're trying to fit some model to something, whether it's clustering or dimensionality reduction or it's regression, well, the model may not exactly fit the data. It's off by a small amount, but if every data point is like this, and then you have to deal with it. Whereas spurious reading, or kind of something like an outlier, would be something that is way off, right? And so this sort of error, if you're careful about it, it will kind of cancel each other out in aggregate over a whole bunch. And this is not considered bad so much, but we should be careful how we deal with it and how we distinguish between that and the spurious readings. And then the third type, I would think, was like the background data. Okay, so the idea here is that you're trying to measure to some feature, and you get kind of this stuff instead. Okay, so think of you're sensing some spatial region or a picture of something, and there's some sort of feature that you're trying to find in red, right? So there's this big astronomy project I'm part of. We're trying to analyze, and we're trying to find this red feature, but you kind of draw this window that you're sensing around, and so when you're sensing, you're picking up all this other stuff in the background. And it's kind of smaller, but it's not necessarily measurement error. It's something that's there. It's not really a spurious reading, but it's something in the background. And so I don't want to deal with the blue stuff when I'm trying to find this red feature, right? So there's some feature that I want to find, and this stuff is in the background. Okay, and it's not flat. It's kind of, there's some ambient stuff happening here. This could also happen if you're trying to kind of get some movie kind of recommendations of something, and you're trying to target people who you think are in the demographic that would watch your movie, but you get some other people in the background. You thought they were maybe in your demographic or you're targeting, but they're close, but then they're not right, the people you're actually trying to target. You get some other people kind of in the background when you do this. So it's not just a spatial thing, it can happen in these other settings, right? So you're trying to measure one thing and you kind of pick up some elements of something else in the background. We'll kind of maybe talk about some of this stuff in the anomaly detection lecture on Wednesday as well. So kind of, I think it's useful to kind of have these three kind of ways that noise can appear in the data you're sensing, and how you treat them is going to be kind of different. The spurious readings are these outliers, which will be the main topic of this lecture, which you want to kind of, we're going to try to identify these or come up with ways of estimating things that are not affected a lot by the outliers. With the measurement error, you want to kind of model this and factor this in, but it doesn't have to be a problem if it averages stuff out. And then the background data is stuff where you kind of want to be able to detect where's the interesting feature versus the background data. Or maybe we're going to be adding in some more background data to hide the features with some privacy preserving things. So and so understand this sort of trade-off. Okay, so let's talk about outliers. And so if we had data, right, let's say we have data in RD and we're trying to run a clustering algorithm or dimensionality reduction algorithm or regression or nearest neighbor search, and there wasn't any outliers we had to deal with, a lot of these problems would be much easier. Kind of for instance, think if we're trying to do dimensionality reduction and we're using like a PCA-based approach, and all of the data lies on exactly a low-rank subspace. Then what we can do is we can write this data down as a matrix, and we can take we can take the principal component analysis of it, and the principal values or the singular values after centering are going to drop to 0 exactly after a while, right? Or there's going to be a clear cutoff between where they're large and then they drop to almost nothing because there's just like the measurement error. And this is not always the case, and we have to make these challenging kind of decisions on what to do there. And so kind of the outliers are the kind of the cause of this problem, but at the same point, if we have the outliers, then how do we actually trust the model that we're fitting in the first place? So kind of there's this challenge, and there's this kind of obvious algorithm or kind of way of removing outliers. And so it's kind of dependent on the choice of the model. So the goal, again, the goal is to fit let's say a model M of X, right? So there's some model so that it best represents the structure that we're trying to find. Again, could be dimensionality reduction, regression, clustering, something like this. And so how would we try and remove the outliers? One, we're going to build the model from some family of models. We choose the family of models, and we want this to be kind of the optimum for M of X, right? There's some sort of cost function that we're optimizing, right? So we're going to build the optimal model on the data, okay? Then we can, for each X in the data set X, we can measure the fit M of let's say xi minus xi, right? So this would be something like a residual, right? So how closely does the model actually fit this data? And then we can say if this let's call this Ri. If Ri is too large, right? So usually we define a threshold, then mark xi as an outlier. Okay. So if we can, all right. So hopefully this seems like a fairly obvious strategy. We're going to build a model. Then for each data point, we're going to see how well does the data fit to the model. If the residual of the fit is too large, we can set some sort of threshold. We need to set a threshold tau or something, right? So if Ri is greater than some threshold tau, then we mark the associated point as like an outlier. Okay, so this seems like an obvious way to identify outlier, and this is pretty much how you should think about it. It depends on the model. So if I chose a different model, let's say I did this with clustering, and then it's going to be different things categorized as outliers as if I did something with dimensionality reduction. The choice of the model is going to tell you which ones are possibly the outliers in this setting. All right, so this seems pretty simple and straightforward. And, you know, there's like I don't know, it's not a secret or anything, but this works a lot of the time. There's maybe not a lot else to say here, but I'll say some stuff for the rest of the lecture. Well, let's think through, though, when would this not work? Why would this not be the right strategy to use? Yep.
You don't have the label, then you do this. I mean, how do you know the outlier is the outlier?
Yeah, okay. So label, like I didn't, if you have like labeled data, so you're doing like regression or classification or something like that, then yeah, sometimes the residual and the fit depends on the label. Where this is more of a supervised learning sort of issue that we have gotten into the last couple of lectures, but for the rest of the class and semester, we're mostly talking about unsupervised problems. So then we have either clustering or dimensionality or things that are unsupervised, and we don't have to worry about labels. Okay, so I think you can think about this in the context of unsupervised settings, and then the label isn't an issue. So when else would this not work? What else could go wrong here?
If you pick the wrong distribution, or the distribution of data is
yeah, so I didn't quite, okay, good, we're getting on the right track. So I didn't say a distribution. I did say this is a family of models, and I kind of was maybe implying this is dimensionality reduction, or this is rank, K dimension down to rank K, or it could be a type of clustering, could be density-based clustering or K-means clustering, right, with a specified number of clustering or other parameters. That could be what's specified here. And so if I pick the wrong model family, then it's just not going to fit the data. I know, or if I pick the wrong way of measuring the distance between data points, then this may not fit the data very well. And some of you in your class projects have been trying to kind of use these techniques, but you're not really finding the structure you're looking for, then what does it make sense to be kind of like an outlier in the setting if I haven't modeled the data correctly? Yeah, okay. So this is a fair critique. Okay, one did not model the data properly. So the wrong model family. This is the script M. And okay, and this could be things like the choice of the distance, the parameter K, kind of dimensionality reduction versus clustering, right? So these are all things I could have chosen wrong. That's not really a good fit for what the data looks like for where it's coming from. All right, so sometimes I want to find clusters, or I want to reduce the dimensionality so I can draw a picture, right? So, but if I have an outlier in there, it might get in the way of what I want to do, right? All right, so what other critiques could I have? Yeah, so if I choose the wrong model, but then I could try, we've only actually thought of like a handful of classes of models I could try here. And so I could try one from each class. And if they don't work for any of them, maybe the distance is wrong, but if I don't have a good way of bootstrapping the distance, I'm kind of in trouble anyways. What else could go wrong here other than the choice of the model family? Doing what? The threshold. Okay, yeah. So, okay, so the threshold, what do I describe as being too large? Right? So I could either be kind of too aggressive in filtering outliers and throw out some good data, or I could be not aggressive enough and there's something which is causing is not from the distribution that's not there. Yeah, this is so I can choose the wrong threshold. Okay. All right, we're losing people to help come up with the answer I'm looking for here. So it's going to rely on more of you, or maybe I should write down the right answer and then move on before they get back. So there's kind of a couple of other, there's like one other big issue with this process. That's is kind of okay, you've hit on points which are true, but those could be said about kind of any other part of the class, right? What is specific about this process for finding outliers that could go wrong here? So how do I quantify if something's an outlier? Let's kind of go backwards. I have some threshold. I say something is too big, right? Usually you can be fairly conservative on saying something is too big. It really needs to be way out of distribution for it to really matter. Okay, so let's say if I had a good way of getting a residual, I can look at all the residuals, and if something is twice as big as anything else or more, that's really when it would probably start to cause an issue. Maybe 5 times bigger residual than everything else. So this is not too sensitive. So let's go backwards. How did I get this residual? Okay, I measured the fit onto the model, right? So for k-means clustering, this might be the distance onto one of the centers, right? For dimensionality reduction, it's kind of maybe the distance of the projection or some distance which is not preserved really well from the true distance before. So how am I measuring this residual? Taking the data, and I somehow, again, the choice of the fit, how we measure the fit, is kind of from the model family. Okay. But it's the fit to the model. Okay. And I found the model which optimized on this data set, but the data set may have contained outliers in it. And so the problem is what? Well, if the outlier is, yeah, so here I fit the optimal model onto the data I had. But if the outliers were in there, the fit to the model is not necessarily the right model to fit because it got messed up by the outliers. And actually, if the outliers did not mess up my model, then I don't need to worry about them, right? So the whole point of the outliers is that they would mess up the fit of my model. Otherwise, I don't need to do the rest of this. Only if I suspect or I'm worrying that my model fitting got messed up somehow. Otherwise, like we did the rest of the semester, we fit the model that best fits the data, and we're like, okay, we're good. We have the model. We use that to analyze what's going on. Okay, so the big potential problem here is that the model we fit equals the opt of M in some class of models is kind of messed up by the outliers in X, right? So if we didn't choose a good model to start with, then when we're measuring residuals, those residuals are not accurate, and then we don't have a good thing to compare them against, right? So the whole worry is that the outliers messed up the model, but then how do I find the outliers if I'm measuring against the model which has been messed up in some way, right? So maybe the outliers caused the model to change, right? I'm running a clustering algorithm and there's one data point really far away. Well, I put the center at that outlier point, right? So if I have clustering here, right? And even I know that there are 3 clusters and I fit. So this is S1, S2, and S3. S3, this set of the centers is my model. Okay, this was the outlier. Right? So this guy is the outlier. But what is the residual of this data point? It's going to be 0, right? So I can't, if I measure this point, I try and filter the outlier by its residual. The residual is going to be 0, so I'm not going to identify this as an outlier, right? So this does not always work if the model fits to the outlier, and then I can't use this to prune which ones are actually did not get fit well, and that means that they're outliers. Okay, and so this is only a problem if I should have picked 2 clusters here, but instead I wasted one of them on this outlier point. There were actually 2 clusters here, but I had to fit them by 1 cluster. Okay, so this is kind of the root of the issue here. Okay, if the outlier isn't so bad, it's kind of in here, then I'll still fit the right clusters, and then okay, it's fine. Right, I'll still group the points correctly, and it's not going to be a problem. But if it's so bad it changes my model, well, then those are the outliers I actually care about, and I'm not finding them. All right, so then what should we do? Okay, so what happens? What to do if outlier changes our model M star? Right, so we're trying to optimize some function, finding some model, but because it was in the data set, it changed what the model was. Then how do we filter out these outliers? Okay, let me show another reason why this could be challenging before we start to get to some solutions here. Let's look at the most common measurement noise is the normal distribution, right? So it looks like e to the negative x minus, the true value of x squared divided by some sigma parameter. Looks something like this, right? And so you have the true value of mx, right, of the actual optimal model, and there's a distribution that looks like, this is a poor drawing of the distribution, but this it's this bell curve shape, and you have roughly 1 standard deviation here. So most of the data is near here, is near the true value, but there's a distribution of the actual observation x, which can get very far away. Okay, and you can look at this distribution and say about kind of 1/3 of all points falls within one kind of standard deviation. Okay, if I go out about 2 standard deviations, so in this region, kind of here, okay, I can say about sorry, this was 2/3. About 2/3 of all points are within 1 standard deviation, about 95% within 2 standard deviations. I can say about, if I go out 3 standard deviations, right? So out to here, this gets about 99.3%, right, of the data is within 3 standard deviations, right? But there's always this normal noise, which is kind of the most common noise, and it's what that, if I look at the data from I'm doing a least squares fit, that can be derived as the optimal kind of maximum likelihood estimator from normal noise. I'm going to have some probability of getting data further and further out. I can't say data really far out has to be an outlier. It may have been just the standard noise I'm observing, right? So if it is normal noise, there's going to be some chance of getting some data out here, right? So there's always some chance of far data. I can't rule out the far data. It turns out, if from a kind of a Bayesian statistic point of view, this is really helpful, because it means that if I have data, I can fit it to the model and I can calculate, well, this data is less likely than this data. Okay, so the further away it is, the less likely it is. There is some way to kind of quantify that, which is good, but it means that I can't rule it out being from the actual distribution. And so if I generate enough data, I will eventually get data way out here in the tail. And so is that an outlier if it's way out here in the tail? But I knew I'd expected, say, 1 out of 16,000 points, I expect to be within four standard deviations, right? So if you're trying to write down like a p-value, right? So you've probably to learn what hypothesis testing and p-values and stuff are, right? A p-value of 0.05 basically says, well, this event would occur under my random baseline model only about 5% of the time, or that or worse 5% of the time. But that means if I repeat this observation 20 times, I expect to see roughly once that like actually like actually that far out, right? And if we're dealing with lots and lots of data, you expect to see some data way out in the tail. This is not abnormal. It comes from the distribution. And if you model stuff correctly, it should fit, right? So we can't just say it's very far away. We should exclude it. We can't. I mean, it's usually fairly safe to do that anyways, because that data is rare. But we can't necessarily say, okay, this is a spurious reading. It could be the normal sort of measurement error that we actually said we were going to model. All right, so this kind of choosing this threshold is kind of not as, necessarily as obvious as you might think it is. Setting a p-value of 0.05, you're going to identify things as outliers, which are actually kind of part of the normal observation. So that may not be so easy either. But for the purpose of trying to build a model that represents most of the data, it's probably okay to throw stuff out more than 3 or 4 or 5 outliers, 3 or 4 standard deviations away. That should be fine. Okay. Okay. So how do we find what? Okay. Let me say one more thing about why this is high. In high dimensional data, this gets even worse. Okay, so now we're dealing with X in RD, where D is, say, very large, and X is let's say IID from a D-dimensional normal distribution. Again, this is proportional to e to the negative X minus some. In this case, the mean is 0. And so just from this distribution, there's some normalizing coefficient in front, which is a mess. I'm not going to write it down. Okay, and so now we're trying to say, what is I want to understand, and the data should be at 0, right? So I'm saying that the data, there is some very high dimensional kind of setting here, and the data should be centered around 0, but I'm going to get data that is kind of roughly a distance 1 away from this data, right? So I kind of want to look at the expected value, and so I can maybe this will be more illustrative to plug in a value mu here, an unknown value mu that I'm trying to estimate. Okay, so now this point is mu. It's a high dimensional value I'm trying to estimate, the mean. This is a point in RD. And so I'd like to understand the probability of the expected value of how far I expect to be from this mu distance. So I'm trying to estimate some parameters, and I get an observation. And so how far is my observation from the parameter set? I'm D-dimensional parameters I'm trying to estimate. Maybe this is the mean of k-means clustering. But the math looks roughly the same if I'm doing dimensionality reduction. I'm minimizing the squared errors or least squares regression. It's going to look roughly the same, but let's look at just estimating the mean. And it'll be easier to look at this at the squared distance here. Okay. What do I think the expected squared distance would be? I set the standard deviation to be 1 in each direction. So I set the standard deviation to be 1 in every direction. So I think every observation I pick should be about a distance of 1 away, right? Well, it turns out that this expected distance is actually going to be, squared distance is actually going to be d. Okay, every coordinate is independently from a normal distribution. And that means that I have d of these coordinates. And so each one is an expected distance away 1, and I have d of these coordinates. So when d is large, the expected squared distance by the Pythagorean theorem is going to be d. Okay? So actually, as I get higher and higher dimensions, this gets kind of harder and harder to estimate. Well, let's say instead, I now do say, well, this is going to concentrate. I'm not just going to pick one thing. I'm going to pick the average. Okay, so instead of x, I'm going to do 1 over n, x and x. I'm going to take this average here, right? This is the x bar, okay, minus mu. Okay, so this should concentrate by the central limit theorem. As I get more and more data, this should get a better and better estimate, right? And this is true, but it looks like d over n. Okay, so as n gets bigger and bigger, the error is going down. But if my dimension is also very large, so I'm in like one of these feature spaces for kind of these large language models work in, how big, and the dimension is, so it's like 2,000 or something. And if I only have like 1,000 estimates, this error is pretty large still. Okay, so if I'm in a high dimensional space, even estimating the mean with concentration measure with no outliers is on average going to be large, right? So it's going to be really hard to get a good estimate of these things if I have normal noise distribution, which is kind of the baseline assumption here. Okay, so even kind of getting a good estimate of the model can be kind of tricky. So I'm going to need to assume, so you kind of need to assume that n is much bigger than d, which is not always the case when dealing with high dimensional data. Otherwise, I'm not going to be able to say I get a good estimate, and then how do I filter out the outliers here? There are other models I can say if instead I know that there's a maximum distance away from the true value, and for instance, I normalize all of my data points in my high dimensional distribution, then I don't get the d effect here. Okay, so if I normalize first, then I actually don't get dependence on d. There's some, but if I assume a normal model, I have to get this dependence on d here. Okay, so this estimation can be kind of hard and filtering out these outliers. Okay, so we're going to try and do it anyways. Let's see what we can do. Let's start by saying, let's do mean estimation in RD, but I'm going to assume n is much bigger than d. So maybe d is 2 for the purposes of pictures, or is 10, and n is like 1,000 or like 1,000,000. Okay, so in this sort of setting, I can start to say something interesting. And there's kind of, so then what's going to happen is I'm going to have some true value mu, which is the mean. I'm going to have a bunch of these observations. And so I might get an outlier here. Okay, so now what would happen is I might get mu hat, might be an estimate here, right? So this would be my estimate. It's pulled away by this outlier. Okay, so what should I do in this sort of setting? Prune. Okay, how do I prune it?
I don't know. Brute force?
Okay, let's say it's 3 dimensions. I can't draw a picture. If I 2 dimensions, you should draw a picture and look at it, and then you can circle the outliers and throw them away. This is what you should do. But let's say I'm in 3 or 4 or 5 dimensions and I don't trust being able to draw it. how do I kind of procedurally do this? Do you think the algorithm we wrote at the beginning, that three-step algorithm, is going to work here? Where we fit a model. This is my model. I measured residuals to this point from all the data points, and then I threw away ones which are much further than all the other ones. The points with the residuals are much higher. Is this going to work in this case? Yeah, in this case, it actually works, right? So I'm going to do kind of one model mu hat to the residuals and three prune of the large residuals. If I drew a ball here of this radius around mu of, or r, or let's say it's this is a threshold. All these points are inside this threshold. This one is way larger than this threshold. This would actually work. Okay, so this algorithm actually worked here. It would have to be, for one outlier, it'd have to be really far away to actually throw off the model. Okay, so this is actually, in this setting with one outlier, this is fine. The problem, and then, okay, there's one more step I should do. Number 4, in this case, goto is not considered harmful, but so I go back to step 1. Okay, once I remove this outlier point, I can recalculate the estimate of the mean, and now it's going to work and concentrate well because n is much bigger than d. Okay, so this case, it actually worked fine. Once I remove outliers, I can go back and fit the model again. Okay, so this is not the hard case, okay, for estimating the mean. What is the hard case? The hard case is these are hard. These are some hard outliers right here. If I look at this distribution, let me draw this again over here. This is the true mean. Okay. Okay, these are the inliers. Okay, and then these are the hard outliers. Each individual one of these points looks like it could be inside the distribution. Okay, but the problem is that with these, I could estimate mu hat is going to be pulled sufficiently far away that it's not going to concentrate. If this is like 10%, 5% of the data, I'm never going to get my true mean to be close, my estimated mean to be close to the true mean. I will kind of have some sort of gap. That can be sufficiently, it'll be like a constant of this standard deviation. So I'm going to get the wrong fit to the data, and this is not really the underlying model I want. Okay, so it's not like catastrophically bad, but it's bad enough that I'm not really approaching the true value. Okay, so this is the hard case where I want to get a really good estimate, and I should get, as I get more and more and more data, to be able to do better and better. In machine learning, we want to get 99.9% accuracy on the classifiers, right? But if I have this issue and 10% of the data is here, I'm never going to get more than 97% accuracy. I'm going to get stuck because of some outliers in the data. They each individually looks like it might be part of the data, but the problem is there's a bunch of them and they're clustered all in the same spot. Okay, and this is pulling the estimate towards these hard outliers. Okay, so this turns out to be kind of the hard category to deal with here. Okay, so how do we deal with this case? This is specific to mean estimation, but effectively the strategies for this work for anything that's kind of like an least squares fit. You can convert them into some sort of like mean estimation problem. Okay. I don't just want to look at the mean, but if I believe that it is normally distributed, which is kind of the underlying assumption here, then I should not know just that the mean should be concentrated, but that also the covariance should be concentrated. Okay, so I believe that X is from a normal distribution with mean mu and identity covariance. And so this should mean that I can create a sample covariance. Okay, this should be 1 over n, X in my data set, and this is X minus mu hat, X minus mu hat transpose. Okay, so I can take an outer product of everything with my estimate of the mean, and this will give me an estimate of this covariance matrix, and it should look like the identity. Okay, if it was really a normal distribution, or it should look like a scaled version of the identity. If it's, I don't necessarily need to know that its identity could be some scaled version, but it's not supposed to be kind of different in the different coordinates. Maybe I did distance metric learning and I have it so that the data should all be on roughly, error should be equal in every dimension here. What's going to happen then? When I have these hard outliers, what is going to happen with the, and enough that it pulled the mean over, then what is going to be different about this covariance matrix? What would go wrong with it? How do I think of a covariance matrix? What are the elements of it that I like to think about, that we talked about in the previous few weeks? The square matrix, how do I analyze it? What is its self, its essence? Yeah, the eigen decomposition, eigenvalues and vectors. Good. You got my hints. Good. All right, so I want to then look at the eigenvectors or the eigenvalues of this estimate of the covariance matrix. They should be all about equal to 1, or they should be all about the same value. If I don't know what the covariance is supposed to be, they should all be about 1. And so if it's large enough that I pulled the estimate of the mean in some direction, then what's going to happen is that the first eigenvalue or the eigenvector, this is the top eigenvector, it's going to be pulled towards these outliers because there's more mass here, and also I've shifted it, so more mass up here as well. And the first eigenvalue and the associated eigenvalue is also going to be larger than 1. Okay, so if there is enough outliers that are biased and clustered that are enough to change my estimate, then when I do the sample covariance and look at the eigenvalues and eigenvectors, these should be noticeably shifted towards this mean. And I should be able to detect this. And it's true that if it's enough to pull the mean, these will look off. And then I can actually detect them. And so this kind of solved this technique, and I won't go in all the details on how to do it. Once you do this, then you can prune the most extreme points in this direction and iterate that calculation. And eventually you will converge to a good estimate of the mean. Okay, this technique is a fairly new idea that was really worked out in the last 10 years, and we really kind of made it practical in the last 5. But this actually works well. This works in very high dimensions. It can be done efficiently, and it kind of combines estimating the mean and the eigenvectors and identifying, okay, we can find a threshold where the first eigenvalue is much bigger than all the other eigenvalues. That means that along the direction of the top eigenvector, I can prune stuff. I can always find some stuff to prune, and then I repeat the calculation. If I iterate this a few times, it will converge to the right answer. Assuming the inliers came from a normal distribution. It can happen up to like 30% outliers, and this will always converge. Okay. Okay, it's a bit complicated and a bit technical and nuanced to get working. So I'm going to tell you about some other simpler approaches to implement instead that can have similar sort of guarantees. But this was kind of the first way we figured out how to do this for multidimensional settings. Okay. Let me jump back to what's called robust estimators. And so instead of fitting a model that's a least squares estimator can be fooled by outliers in this way. So what if we just build a better estimator that can't be fooled by outliers? Okay, so the idea is to build a better estimator, not fooled by the outliers. Okay, and so the kind of the historical best way to think about this was through what's called the breakdown point. And it's the idea of the breakdown point is, the definition is either going to be a little informal or very technical. I'm going to go with the like slightly informal version, but is basically how many outliers needed to kind of move the estimator very far. Okay, so the technical definition involves thinking about infinity and stuff like this. Okay, but how many outliers do I need to move the estimator like very far from where it's supposed to be? If it's not moving very far, it's probably good enough. Okay, so what does very far mean? It's far enough to matter. Okay, so again, so the informal, but it gets to the main purpose. Okay, so let's say for a point estimator in d equals 1, okay, what we typically would be doing is the mean 1 over, right? If I just take the mean, this has a breakdown point of 1 over n. So what fraction of the points, or how many should be kind of what fraction? Okay, well, we have a value between 0 and 1 here. Okay, so the mean 1 point can move the estimator. I can send 1 point off to infinity, and the estimator will move along to an infinity with it, right? Okay, but as was, I think, mentioned in the last lecture, if I use the median instead, okay, so I sort and then take value kind of n over 2, this has a breakdown of 1/2. Okay, I can move up to, not including 1/2 of the points, off to infinity, and the rest of the points will still be in the same region, right? So if my distribution is supposed to be in here, and I take 30% of points here, my estimator, the median is still kind of inside the main distribution. Even if 30% of points are moved off to infinity, the further away I move these points, the median is not going to change because it's dependent on the sorted order in the one dimension. Okay, so the median point has a strong breakdown point of 1/2. 1/2 is as good as you can get because if I move more than 1/2 of the points, all concentrated together, well, then that's the better representation of the distribution than the ones I didn't. Okay, so I can't do better than 1/2. Okay, so actually I want this to be, the value is going to be between 0 and 1/2. Okay. Okay, so in one dimension, the median is this nice robust estimator. I can use it instead of the mean. If it comes from a symmetric distribution, like the normal distribution, the median will be a great estimator of what the mean of the distribution is, in fact. Okay. Okay, so we would like to do a median to replace the mean, but in high dimensions. Okay. Median in high dimensions. Okay. Okay, so how do I define a median in high dimensions, like 2 dimensions even?
Maybe we should.
Okay, I can take the norm of the points. Yeah, so I can reduce it. Okay, so I can take, so how do I create the estimator? Do I sort them? So I take the point with the median norm. So what I could do is I could have that this depends on the origin, and then I could have a set of points off here, a set of points off here, which are outliers, and then one point, which is here, and maybe this is the median norm point. So this is my estimator. But the distribution is over here. So I don't quite see how to make this work. It's an interesting idea, but the geometric median. What is the geometric median? Great. Yeah, okay. So the geometric median is the right name to use. This is equal to the arg min of P in RD. That's minimizing the sum of the xi minus P. Okay. So it's the point that minimizes the sum of the distances, right, to all these data points. Okay, if it was the sum of the squared distances, this would be the mean, but the sum of the distances is called the geometric median, or the L1 median or something like this, right? And this is what we use for K median clustering, right? This is the point that we put at the center of a cluster of points for K median clustering. And okay, indeed, this point is going to be more robust to mean. It won't necessarily converge to the right mean if we have this hard sort of distribution, but it won't be too far away. So it won't quite solve this issue when I had these clustered outliers, but it's going to do a pretty good job if there are not too many outliers. Okay, so this will work well. This works if not too many outliers. Okay, if there are like 10% outliers, this might not work. But it's a good. This is one way to generalize the median to high dimensions. Solving this problem exactly is kind of tricky. I can run gradient descent on this, and there's something called Weisfeld's kind of algorithm, which runs gradient descent on this function. It's not strongly convex, and there's actually a bunch of weird cases you have to worry about here. It's kind of strangely messy to work with, actually. It's But you can get this to run. You can download some code. There was like a recent theory paper that said we can approximate it with an epsilon in near linear time, basically. But it's messier to run than just calculating the mean, but this works pretty well. And usually without too many outliers in high dimensions. All right. It doesn't, I don't know if you can say something formal about the breakdown point of this, right? So I could have 10% of outliers and I could really mess this up. I don't remember the example right now. There's another algorithm. There's another extension called the Tukey median. Okay, and so this is a point with large so large depth, and in fact with the largest depth, and I'll need to define what depth means, but it means that it's kind of defined by the convex hull of the point set. So I kind of want to do something, think of like identifying the convex hull of the point set, and then I can kind of think of removing all these points and then finding the next convex hull of all the points which are remaining. And there are a bunch of different ways to define depth. And so eventually I want to find a point kind of in the middle here. This point should be something like this. It would be robust. Now, this is not actually what the definition is. What I want is I define the depth of a point P with respect to a data set X, as I want to think of, so I've got a data set X, okay, and I'm going to consider a point P, and then I want to look at the direction U, and I want to say what fraction of points can I have on one side of some half space, or I project onto a direction U and I sort them, and I would like P to be the median, right? I'd always like it to be the median in every direction I project onto. I can't always do that, okay? But I want to say I would like to be as close to the median as possible, meaning on any direction I project, there are always a large number of points in every direction. That fraction of points in every direction gives me the breakdown point. I can't have too many points out, and if there aren't too many points out in every direction, then I can't be pulled to. Those are the outliers that could be pulling the point that's far away. Okay, so the depth of P with respect to X is the maximum fraction of points separable by a half space, and we'll call this H of U because it's defined by a direction U, over all choices of direction U. Okay, so if I picked another point up here, well, then the direction would be pointing in this way, right? So I'd like a point that no matter which direction I pick, I can't cleave away a large fraction of the points with the half space. Okay, and so then this is the depth of a point, and so the Tukey depth is, yeah. So this would be called the Tukey depth. There are other ways to find the depth, and so then the Tukey median is the point P with maximum, so Tukey depth. Okay. What's known about the Tukey depth is the breakdown point there are two things I can say. One, the breakdown point is always 1 over d plus 1 is always greater or equal than 1 over d plus 1. So in 2 dimensions, it's going to be 1/3. I sometimes can't have more than a breakdown point of 1/3 in 2 dimensions. If my distribution looks like a triangle, then for any point in the middle, I can always chop off 1/3 of the points in the triangle. And in d dimensions, I can have kind of like a d-dimensional tetrahedron with d plus 1 corners. I can always chop off just one of the corners. I have more room to place these points. But this is as good as I can possibly do for breakdown point, and also converges to mu star of inliers of inliers that are drawn from a d-dimensional normal distribution. It will also, if I draw points, inliers can be d-dimensional normal, I have some fraction of outliers, it'll actually, that's less than 50%, it'll actually converge to the right thing. The problem is this is very hard to compute. It's kind of pretty slow to compute the point with the highest Tukey depth. So this is a very powerful estimator, but it's harder to compute again. So I can define it. It's a little complicated, but not too bad, but it's hard to compute this. Let me write down a simpler algorithm that is very effective in practice. The median of means. Okay, I'm going to choose, this can be for x in RD, where n is much greater than d, and let's say k is less than d. Okay, it's a pretty simple algorithm. I'm going to randomly split x into subsets, x1, S1, S2, up to Sk. So I'm going to randomly split x into the subsets. I'm going to compute the mean mu j of the mean of each of the subsets. And then I'm going to do a coordinate wise median of the set mu1, mu2, up to mu k. Okay, so I'm going to look at all these means of subsets. Okay, so if I just do the coordinate-wise median of all the data sets, some weird stuff can happen, it turns out. If I do the coordinate-wise median may not be in the convex hull, it might get fooled in various ways. And so k can be like small, like 5 or something. But if I first randomly split it, take the mean of every subset and take the coordinate-wise median of these means, it turns out that this has some nice properties. So because of the median, if d is much less than n and k is less than d, I think the breakdown point is high, and I think this in a lot of conditions will converge into the right answer. Okay, so these are ways of dealing with the mean estimation. I want to mention, before we wrap up, I want to mention 6 minutes left. Two other approaches. Yeah. It's not. It's every coordinate. I sort them in that one coordinate and take the median in that coordinate. Okay. Yeah. It's a good question. Sort in each coordinate. Okay. Okay, I want to mention 2 other approaches. This is a parameterized approach. So I want to mention quickly that there's these other approaches based on density-based clustering, and we talked about the DB scan algorithm, right, from the hierarchical clustering. Remember, this one had a very different model of the data, and it said there were these dense regions where I could take a ball, and if the number of points within some radius r, if the num points is greater than this parameter min points, then I would say that means that these are going to be inliers. Inliers, okay? So then I can identify a bunch of points here as inliers, and then any point kind of close within a radius r of the inlier. And this defines some region where the density is high based on this radius. And then anything else, these points then are going to be these outliers. Okay, so this density-based clustering does not have a specific model that it's fitting. It's saying if the density is high based on some radius, and then the number of points in the radius. So I have to set these parameters in order to define what it means to be close and how many points is enough for the density to be high. But this is another way that doesn't depend on some underlying model and distribution. I could also do something where I build a kernel density estimate on top of here, and if the density estimate is higher than something, I say it's an inlier, otherwise it's an outlier. Okay, these are other models. The problem with this sort of approach is that it assumes a uniform, this assumes a uniform, density. And what often happens in messy data stuff you've dealt with is that the data will be denser in some region. As it gets towards the boundary, it gets less and less dense. And where do I draw this sort of threshold? And so those points where it gets to the boundary aren't necessarily outliers. It's just getting more spread out. The last method I'll mention only requires a good notion of distance and is quite effective. Reversed nearest neighbor. Okay, so I only need a kind of a distance function d. Okay, and so what I do is for all x in x, I find the kth nearest neighbor. So let's say p equals phi of x, the kth nearest neighbor of xi. Okay, and then I also find, so then I compare. I say xi is an outlier if the distance from xi to its xk of xi equals p is going to be much bigger than from the distance from p, which is its kth nearest. I could do nearest neighbor, but kth nearest neighbor is a bit more robust. So if I look at its kth nearest neighbor, okay. So if a data point is an outlier, if there's a distribution here, even if it kind of fades, and then there's a point up here, the distance to its kth nearest neighbor, if that's much further than this point's, so if this is the point P and its kth nearest neighbor is in this radius, this distance is much further, then I would say xi is probably an outlier. So if it's not symmetric, but if the distances are close, this can adjust to the local kind of density of the data. And so for messy data, when you only need have a distance, and this reverse nearest neighbor is a pretty good trick to actually prune stuff out and adjust the density. I don't need an underlying model. I just need a distance that I trust. Okay, so this is what we'll say about outliers. We saw a variety of techniques. Some, the more really, this is an old idea. The robust estimators, there's a bunch of modern, very modern work in that. We kind of did that in the middle, but hopefully bookended by some really practical and useful techniques to kind of identifying your outliers here. All right, we'll stop here. Let me turn off